our last speaker, Tommaso. Ranzani, if you can share your screen.
Hi, yes. Here we go.
Yeah, we can see your slides, not in presentation mode yet, now in presentation mode, and we can hear you. Thank you.
Thank you. Thank you so much for the invitation. I'm very excited to be here talking about the research that I'm doing in my lab at Morphable Biorobotics Lab at Boston University. I want to start just giving a shout out to my students here. We work on a variety of different research topics. If you're interested in more, just feel free to reach out or look at our recent publication list on the website. Today, of course, for the time constraint, I'll just focus on one specific project that we're doing in the sort of field of intravascular beating heart surgery. So we're specifically looking at developing devices that can operate inside the beating heart. And there's a strong clinical motivation. There's a lot of procedures that are done a lot of cardiac procedures that are done every year in the United States. And a lot of these procedures still require what's called an open surgery approach, which is a very invasive approach, requires direct access to the heart, so opening up the sternum, stopping the heart, having extracorporeal circulation, which is, of course, again, requires long recovery time for patients, and a lot of patients that suffer from cardiac conditions may not be eligible for such an invasive procedure. And so the minimal invasive alternative to that entails the use of catheters, and catheters are these very small sort of tubes that you can use to navigate from peripheral access in the vasculature until you reach the heart. But you can easily imagine how this thin tube can provide quite limited dexterity and force transmission in such a highly dynamic and complex environment like the heart. And we specifically identified three really exciting kind of engineering challenges that entail operating inside the beating heart. And there are the size discrepancies. So you need to have your device small enough to access the vasculature through a peripheral access point. But then once inside the heart, you have a way larger workspace to operate in. The workspace is moving a lot. Of course, you have moving the muscle contraction and the blood flow. And of course, remote tool operation. So basically the mechanical ground for your device is at the insertion point, which could be very far from the point where you're actually applying the forces. And this is, of course, limiting force transmission. And so our approach in tackling this has been to develop a soft robotic platform that can sort of stabilize at the entrance of the heart. In this way, sort of shifting the fulcrum closer to the point of application of the forces, and then exploiting a sort of soft robotic technologies to improve dexterity and force transmission, but even stability inside a highly dynamic environment. And this is the platform that my PhD student Jacob Rokatinsky developed during his PhD, and is basically designed to be compatible with the constraints, of course, of the surgical scenario in terms of compatibility with imaging, materials, and so on and so forth. So for this talk, I'll just focus on sort of the functionality of its components. So it has a sort of a soft robot at the distal tip and a stabilization mechanism right distal to that. And so trying to understand the role of these two systems. So we have the stabilization. What it basically does, it allows to improve force transmission distally. So it's fabricated through the compliant mechanism. So by a combination of rigid, flexible, and soft materials layered together in a layer by layer manufacturing process, such that when you actuate it, it sort of folds into this three-dimensional shape. And we tested, of course, that it does what it's supposed to do. So it's able to counteract forces applied distally. You can see here in the performance in the plots we showed that when it's braced, this pink thing over here, it's a tract of superior vena cava, which is the vein that feeds directly into the right atrium of the heart. And it's a pig model of that. And so the stabilization now is deployed, and we can see that we can sort of counteract Newton level forces using this local bracing technique. And of course, being a medical application, we have to check safety. We assess that it doesn't provide any damages to the interior wall of the vein, nor, even more importantly, it's actually causing any increase in the pressure within the vascular system, which could be very, very dangerous. And so we combine this with this soft actuator. We fabricate these soft actuators by a layer by layer process of thermoplastic films here in green with sort of thermally shielding materials, which is generally use Teflon. And so individually laser cut and stack all these different layers. And then by applying heat and pressure, you can selectively bond the different layers across the laminate. And in this way, you can fabricate structure like this one, which is a 3 degree of freedom structure, starts initially flat. Then it can extend depending on the number of balloons that it has. That's the sort of the stroke that it will have. That's why we call it stacked balloon actuators, because it looks like a stack of balloons. They can have multiple multi-directional bending. We demonstrated we can achieve very high power density and force transmission. The other interesting thing about this system, this kind of actuators, is that their deformation is mostly due to the geometric unfolding of the structure. That means that you can model them geometrically, which can be advantageous. And we've developed a geometrical model, and we've integrated that with a sort of constant curvature to have the kinematics of the system. And this is the robot, how it looks like. So we have our stabilization system, we have our actuator, which is, again, for compatibility with surgical settings. It's able to deploy instruments through a working channel and orient in different location. You can kind of see here on this video the role of the stabilization in enabling force transmission and what happens if you don't have that. While here on the bottom, you can kind of see actually tested inside a porcine model. This is being open for visualization. And one of the really interesting things that we sort of were able to exploit is sort of the shape reconfiguration of the system. So because it's just an empty bag at the end, you can actually collapse it radially. And that really allows us to feed it through a small access port, and this way tackling the sort of size constraint challenge. So you can still navigate from very small peripheral access points. And so you can see here now, again, tested to see like if the whole system is able to provide Newton level forces in a sort of a simulated hard environment, and we were able to achieve that. And more importantly, we're able to achieve that without compromising the overall stiffness of the platform. So the system can be as flexible as you want, so you can still traverse like curved path and the complex vasculature without compromising the ability to apply Newton level forces distally, nor the ability to reach any point within the right atrium. We can kind of see here the workspace overlap to a model of an actual atrium of a patient. And so we'll be testing this on a variety of different applications. We're doing in vitro testing, we're doing ex vivo testing. We are currently running in vivo testing on animal models, again, for a variety of applications. The one I want to highlight here, and that I think is particularly interesting for sort of an embodied intelligence kind of perspective, it's what's called tricuspid valve repair. So tricuspid valve is a valve that connects the right atrium to the right ventricle, and needs to repair basically when it's leaking. So some of the blood from the ventricle is leaking back into the atrium. How do you fix that? So to fix it, you can kind of see here on the bottom, most of the cases, they need to do what's called an annuloplasty. So they need to reduce the cross-section of the annulus to sort of cinch the valve and reduce the leaking. This currently in the US, there is no device that is FDA approved that can do that in via catheter. So all of these procedures needs to be done in open surgery, and a lot of the patients that need this procedure cannot undergo open surgery. So that's kind of a big clinical challenge. So why is it challenging to do it transcatheter? It's challenging because to do this, you basically have to place a series of anchors around the annulus and then sort of use them to cinch its cross-section. And placing these anchors is very challenging because the annulus has a large range of motion, a complex range of motion, and a complex anatomy. So it requires a combination of accuracy and ability to maintain constant contact on a moving target. We actually demonstrated, you can see here in this video, with an induced physiological movement in vitro settings, but the system is able to exploit its inherent compliance to maintain a constant contact on a moving target while deploying anchors to then fix our annuloplasty band. And we demonstrated that in vitro, and we demonstrated that ex vivo. Again, there's no active control, it's just the way the system is designed that allows sort of to comply with the motion of the valve. And you can kind of see here a little bit better in these other videos where we sort of try to test this a little bit more. In the top video, you can kind of see we have a system that is probing the robot with a force sensor so you can monitor the interaction forces. And after a little bit, we can see how the robot sort of puts in sync with the motion of the system and is able to maintain constant contact to a sort of a preset level of force. So you can see here approximately 0.5 newtons, which is a pretty exciting results that we're working on. And of course, now we're trying to move this forward and include a little bit of active sensing as well, with some active control by integrating some sensing at the tip, but already being able to do passively. It's pretty interesting. And you can see here at the bottom that this is, again, a result of both the compliance of the system in combination with the stabilization. Without the stabilization, this is incredibly hard to do. And I think the right side of the GIF on the bottom sort of gives you an idea of how hard it is to be done with conventional instrumentation, where the motion of the heart just pushes the instrument back, and it's really, really hard to maintain constant contact. And with this one, I just want to conclude this very brief overview by acknowledging again my research group and our clinical collaborators at Harvard Medical School and Boston Medical Centers, and of course our funding agency at NIH. Thanks.
Amazing. Thank you so much, Tommaso, for this amazing work.